We're really pleased to have Tom Clark from Dordt University in Sioux Center, Iowa. The word Sioux is a very common crossword puzzle clue along with Oreo because of its vowels and everything. And I never could spell Sioux right until I started to do these crossword puzzles. And so now I've got it down pat. But Tom is going to talk to us about falling water and modeling. Sorry, you're on.
All right. Well, thank you for coming, and I think this will be, hosted later, so some people might watch it after the fact as well. So I'll try to be clear. But I've got the chat up in case anyone has a question. Feel free to type it in, and I'll try to grab it along the way. So yeah, so the first thing, building on a foundation, and this is a Semiode conference, and I think it bears just stating how important some of these resources already are. And the work that I'm doing is certainly building on work that was already done. There's several articles already on Semiode and resources and all kinds of things. I'll put some links at the end as well. But just the idea of doing modeling of draining water tanks is certainly, well studied, and Torricelli's law is sort of the key thing that people need in order to do it. So we're clearly building on a foundation here, but I think that there was room for extra work. So in particular, some other tank geometries, what if it's not a cylinder? What other shapes are possible? And the geometry allows the modeling to get more interesting, as we'll see in a little bit. Another thing is, maybe you can get a cylindrical tank, just even using a 2-liter bottle or something. But what some of these more complicated ones, is there some videos available? Did somebody take the time to get a really high quality data set that you can use to compare numerical solutions or analytical solutions to, and see if your model is correct or not? And then I think, but the most interesting thing is just the way that as the models grow in complexity, we can sort of grow in solving techniques. And in particular, what we're looking at here is separable differential equations. And it turns out that all of these models have this in common. And so I think for me, the real value is, if you were going to teach separable differential equations anyway, and you wanted to have some real world models that you could either demonstrate or watch on some of these videos and have real data, this to me is the place to go for that. So a lot of you probably already know this, but just for the sake of review, in case you're less familiar with Torricelli's or you haven't done it for a while, it turns out that you can use physics to show that the velocity at which water comes out the bottom of a tank is proportional to root h. And so there's some nice physics here that I don't really go into, but the physicists do when they take physics. And a lot of my DE students are engineers, and so that kind of connects for them. But what I care about is essentially just coming down to, it's the change in volume is essentially k root h, right? So that's kind of a nice thing. And all the models will build on dv dt equals k root h. That's the water that comes out the bottom of the tank. Well, you've got the bottom of the tank and the top of the tank. And if the top comes down, if the water comes out and the top comes down, the change in water has to be the same, or the change in volume has to be the same. And so if you can write the volume as a function of height, then the chain rule allows you to get, by equating these dv dt's right here, you can get a differential equation with respect to dh dt and this h right here. And so that's sort of the key, is eventually, you deal with volume in the geometry, but at the end of the day, you're getting a differential equation for the height. And once you've solved it, it turns out to be, these are all separable differential equations that you can solve for h of t. And when you drain the tank, you can see the water come down. And so there you go. You can see the solution in connection with something that is actually there for real. So that's Torricelli's law. You can kind of spend as much time on that as you like. And with the rest of my time, just kind of walking through some of the different potential tanks and sort of what we get when we do it. So first, we got a cylindrical tank. it's pretty straightforward. If it's a cylinder, the volume equation is just AH for, area, the cross-sectional area A, and then H, the height. And so when you do dVdt, you just get A dHdt. And so substituting that in, you just get this nice, dHdt. And usually you would just write that as dHdt equals negative, maybe K1 root H. And that's probably a problem you would solve anyway if you were teaching separable differential equations. It's just a nice example problem, and you get a solution that works out pretty good. But you've done it in the context of a real problem that you can actually see happening. And so I do this demonstration in my class. I've got a nice, this is called a resonance tube. You can get one from the physics department. They'll just give it to you if you ask nicely. What's nice is it's like exactly 1 meter high, and the water drains out really nicely. And so you can see, putting lines on the side. Maybe if I can zoom in here, you can kind of see I put lines every 10 centimeters so that they can kind of see, how long does it take to get from one to the next. And you can sort of gather some rough data in class if you like. The water kind of shoots out into a bucket, so we kind of have some helpers here. This was back in the COVID days. Everyone was all masked up, but and you can kind of talk about the geometry of the situation. Water goes down, water goes out, etc. Okay, so this one's, I think this differential equation is so nice, you probably do it anyway. It's not that hard to get the cylinder, so you might as well do that too. And the students really like seeing the water come down. You can do a little bit more, thinking about, is it going to be fast and then slow, or slow and then fast? Or is it just going to come down at a constant rate? A lot of like good conversations. And if you do, a lecture-based class, this can be a demonstration. But if you do more active learning, you can have them, build up these models. The topic works no matter how you're choosing to teach your class. I think it's just a good example. The thing that I think I'm really adding here, people have done cylinders before, but what I did is I videoed this whole process, and then I went frame by frame through the recording. And so I've got a data set that's exact, it's accurate to the millimeter of height and to the second in time. And there's a video of it on YouTube that is linked in the paper. And so if you don't want to do it yourself, you can just show the video and grab the data set, and there you go. And so what's pretty good is when you take the solution to that differential equation and you plot it on the data, it's like a beautiful thing. It's like a work of art here, how the quadratic solution almost perfectly matches the data. The only thing I wish was better is at the end here, you can see that there's this little cap at the very bottom of the thing. And so I can't see the last like 2 centimeters of the data set. There's a little gap right there. But otherwise, it's just tracking exactly perfectly. And the only, I guess you can talk about some parameter estimation. This C ends up essentially being determining the initial height. If T is 0, then C squared has to be the initial height. And then what you can do is you can just sort of say, okay, well, let's just fit K here so that we hit the first 3 data points. And then after that, let it go and see if the model works. And you could do a regression if you wanted to, but that's not really what we're doing. We're kind of saying, like, if this K is right, we should hit those first couple points. And then if the model's right, then we should stay on the data. If the model's wrong, then you'll go off, and you can kind of, play a game around that way. So that's a cylinder problem. That's great. Pretty standard. So let's do the cone. So the cone problem would look like this. And what happens now is this A of H, that height, given a height H, the area at H varies for different heights. So you need to think about when, a centimeter of drained water at the top is more water than a centimeter of drained water at the bottom. So that dVdt starts having an effect. And then you can have the students think about, okay, is this going to be a fast and then slow, or is it going to be a slow and then fast, or is it going to be linear? The cylinder was fast and then slow. is the cone going to be the same or whatever? So you can do lots of little things about, how you choose to teach it, but it's a great problem. So essentially, the only thing you have to change is that volume formula, which if the cone has a particular angle theta down here, which I guess every cone would have some angle theta there, then you can write dv dt according to that equation. It's basically geometry. But at the end of the day, all that stuff really just turns into some constant, and then you get an h to the 3/2. Now, again, we get a separable differential equation. It's a nice one to solve. It's different than the cylinder one, so we're going to get a different solution. You can solve it. You get the answer, and then you buy yourself a cone and drain the water out and see what happens. You can buy a cone like this for $20 on Amazon, or if you don't want to, I've got the video. I did it, and I went through and got the data down to the millimeter and down to the second or half second, and the data set's posted and the videos are posted, so you can just show the video if you like. And what's really fun is when you this would be the solution if you solve that separable differential equation. It's a 2/5 power. I always tell my students, have you ever seen a 2/5 power actually be meaningful in your entire life? I mean, I've never seen a 2/5 power actually have a meaningful answer. And here it is there, and again, the C is determined by the initial height. And then that K is just determined by, you just pick K so that you hit the first couple data points and then you see what happens. And the model's pretty good, but it's not quite as good as the parabola. The cylinder seems to be a little bit more, close to reality compared to this conical model. And so that's a little disappointing. But the students are still pretty happy, and you solved it, and now you get to, do the whole thing. Except, actually, a little trap there. The water doesn't really drain out the bottom of the cone. It's been truncated. And so we never accounted for the truncation in our model. So now you can say, wait a second, we've got a problem. And you can get at what I like to do is that little flow chart of you have the real world, you try to model it, you get a solution, and then you get some data over here. And if the solution doesn't fit the data, then you're back into the modeling process. And so here's a problem. That's no good. The model's wrong. The solution doesn't match the data. And now we loop around in that flow chart. We say, oh, we didn't account for this truncation T. The water's not really flowing out the tippy tip of the cone. The cone's been cut off. And if we account for that in the model, the only thing we have to do is replace H with H plus T. Essentially, that's sort of the substitution we make. So you go back to the model, you replace this H with H plus T, you get a different separable differential equation. And now here's another example of a separable differential equation that's motivated by a real world situation. You can solve it. You can let the students solve it. You can solve, however you want to teach. And when you solve it, the data matches the solution to perfection. And so loop back around, and now you've got modeling hitting reality. It's absolutely incredible. You've never seen anything. There's that 5/2 term that we saw before, but you get a couple other terms. And it's actually an implicit solution, which I think is great because the previous two were explicit solutions, but now you get to talk about what's the difference between an explicit and an implicit solution. You wanted to do that anyway, and now it shows up naturally, motivated by an actual problem that they can literally see with their eyes and watch it come down. I mean, this moment is, they can't believe it. They cannot believe that math is actually this good and that they can be this powerful. It's, I really say it's a real feeling of power to use math to actually model something. And so now you've got three nice examples. You got the cylinder, you got the cone, you've got the upgraded cone, and you might think, that's it. But wait, there's more. There's one more, and maybe you've thought of it. It's the sphere. So the sphere is another simple, quote unquote, simple geometry. And you could, if you want, do the sphere problem. You can give it to them as homework. You can have them try to do it as a project. However you want to do it, you can do it in class. But again, it's the same setup. All you have to do is figure out that volume formula and the area of the height relative to, or that cross-sectional area relative to the height. And you can derive this if you want, or you can just kind of give it to them. It's a little bit messy. Sorry, here's that volume formula. So if the sphere has a radius of r, then the volume of a sphere filled up to a particular height is that equation right there. You differentiate it with the chain rule, you get dv dt. You equate the two sides, and you get, again, this separable differential equation. It's yet another separable differential equation. You see the three halves like we had with the cone, but it's a little bit different. Not impossible to solve, though. The deriving is more complicated, and I've swept some details under the rug here if you want to kind of get at that later. But you get this differential equation. We got the sphere, we filled it, we filmed it, we drained it, we got the data. So the data is posted in a nice data set. There's a video if you don't, it's a little harder to get one of these spheres. So this would be the hardest one to find, but the video is there for you. And there's the data set, and there's the solution. It's again implicit. It's also kind of interesting because the solution sort of does this funny little shape here. So the solution isn't really even a function. It's got all kinds of weird, interesting features going on. It's sort of fast and then slow and then fast at the end, which is kind of interesting. The cone was slow, then fast. The cylinder was fast, then slow. The sphere is fast, slow, fast. As you can imagine a sphere, it's going to be fast at the top and at the bottom, but in the middle, there's all that water. So it just has this funny little S curve, if you will. I've never seen anything like this, but there it is. It's an actual problem that you can do for real, and the data's there, and that's good. So just a couple things just to kind of summarize here. The cylinder, you can talk about Torricelli's law. Very easy to do this in class. I've done it in Calculus 1 before. I've done it in Calculus 2, depending on when you kind of do a little bit of this modeling. But the model's, kind of straightforward enough. Then you do the cone. You can upgrade the cone, or you can start with the upgraded cone if you don't want to do two versions. But I like the bait and switch on the cone. And you can think about, is it going to be fast, then slow, or slow and then fast? And then the sphere adds that more complex geometry, and the data fits the solution pretty much, right on again. So those are sort of the, the motivation, the three examples. And to me, if you're teaching separable differential equations anyway, why not do examples that are meaningful, right? So that's sort of my opinion on it. I've got just a couple minutes left. I want to leave some time for questions, but I'll just share one last thing with just a little student feedback. Just informally, students have, reported that they enjoy seeing that the answer matches the data. They like that modeling allows them to answer questions they wouldn't otherwise be able to. I did give them a survey, and so, you can kind of take this or leave it if you want. But you can kind of see, how important did you think differential equations would be at the beginning of the course? And this is, 95% engineers. And so they thought, well, it'll probably be somewhat important, but you kind of get a little bit of movement over here. After the course, they thought that it seems like it's a little bit more important than at the beginning, which I like to see, and if you weren't doing any real world modeling, they might come away thinking it didn't have any real world importance. So kind of sliding students over one to the right seems good to me. Yeah, this would be these are the shifts. So if they moved one over to the right, most students moved 1 or 2 units to the right. Some students didn't move. I guess one student, maybe one math major, wasn't so happy about all the modeling, and they they moved to the left. But most students either stayed where they were or moved to the right. And then this was sort of another interesting question. Okay, we did a lot of these real world modeling problems. Did that help you learn? Did that make you want to learn? And we're seeing that a lot of students are more motivated to learn because we were doing real world problems that had a connection to reality. But this one is really interesting because you might say, well, are you missing out on the standard topics because you're doing all this modeling? And, we should just go back to the basics of just, calculus with no modeling. Well, they say they learn the regular topics just as well or better. And so the modeling kind of helped them have a route to grab onto when they were, learning even the standard topics. They felt that was kind of valuable. So I thought that was pretty encouraging. I teach 2 sections, so we're looking at maybe 40 students here, just kind of responding to a survey at the end of the class. But it was pretty good, fairly encouraging data. So I got a few minutes here for questions. I appreciate your attention. And here are some of those references. So this is the paper where all the data and the links are in. It's on Primus. And then a shameless plug for another paper I wrote years ago about doing some dry ice modeling that I kind of think is a nice problem as well if you're into these kinds of things. And then all these semiode problems as well that are available. So I think I'll stop there, and then just if you have a question, feel free to either speak up or type it in the chat. Happy to take questions.
So, have any comments, questions? You want to sign up for Tom's class?
That just seems like a delightful modeling scenario. Thank you so much for sharing it.
Okay. I could hear the kind of joy in your voice when you completed the modeling triangle and you went back and reiterated. That happens time and time again every time you teach it, I assume, right? It's like a drug that we do.
It's so satisfying. I mean, I don't think you can get over how fun it is to see that, learning from mistakes, and even, you set it up almost that you're going to be wrong. And so you're modeling that it's okay to be wrong. I think, just as a pedagogical move, students they make so many mistakes. They're wrong all the time. So if you're wrong and then you make it safe, I think that's just valuable for them to see that. And you kind of get my personality. I kind of, juice it up a little bit, but I mean, no matter your personality, I think showing them that loop, it's a loop. I mean, in the real world, nothing is perfect the first time. It just doesn't ever happen that way. So I think they understand that, as, mostly engineers that I teach.
Well, your personality is contagious, and I think that means a lot to students. If you come in excited, at times you come in excited and they're going, what's going on? What's going on? All of a sudden they realize, wow, this is cool. And as opposed to, oh, well, lesson 2, integration by separation of variables, blah, 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 blah. They go, I can sleep through this. How many different shapes have you done in particular? Have you exhausted all the ones?
I mean, I'm happy to do more, but this is all that I know of or that I could get a hold of.
Okay.
The one thing is the upside down cone.
Oh,
I haven't done the upside down cone, but theoretically that would be different.
yeah.
And so that is one that I have thought of, and then I've never gotten around to it. So that would be interesting as well. There is I'm trying to think, and I think it's this one, the water clocks, where you try to find what is the shape of a container that would drain at a linear rate? And I've done that I've given that one as a project before, where I make the students kind of figure that one out on their own. I thought maybe you could 3D print it, but I think it would be difficult to do.
Well, no, I've got Pete Seeberger, who's at Monroe Community College, who's promised me, maybe no problem, just get me the equations and I'll make the 3D printer out of translucent material so you could see it. And the Egyptians knew how to make this water clock, about 1000 BP. And obviously they didn't use differential equations, probably a lot of empirical stuff, but
Yeah.
Yeah, I agree with you. And when you looked at those plots, I mean, when the students look at those plots, it's like in your face, like this stuff works.
Yeah.
And it's not as if, okay, he's got some bogus data set he made up because he knows it fits. It's like, no, we saw it, we collected it, and this works. And what science is about is replication. You got to be able to repeat it over and over and over again. And certainly those of us who've done these experiments can vouch for that.
Yeah. Yeah. And I do, when I do the cylinder, I got the lines on there, and we'll just have a stopwatch set up. And so what someone will do is just every 10 centimeters, they hit the stopwatch. So we'll collect a live data set. Now it's got a lot of error in it because of the nature of the thing, but then, they collected the data, click, 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 right? You kind of see it go down, and then you can just plot that, and you see the quadratic. I mean, it's just as plain as day. And then I say, well, if we had a little more time, we could get the better data set. And then we plot that on there too. But it's, yeah.
The other thing is, you pointed out, you go to your physics department or a chemistry or engineering department, and there's the people who run the equipment closet, let's call it that way, or the equipment room. They never throw anything away. I mean, they just don't. They're the ultimate hoarders. And when you go, at the same time, they're being inundated and they're terrified about an earthquake because they'll be crushed to death. And so if you go in there and say, hey, do you have any meter sticks we could use? Oh, yeah. You want wood, you want plastic, you want metal. I mean, it's amazing what they're willing to part with. And one time I went to a physics department, he says, do you want regular meter sticks or long ones? And I looked at him and I go, I think a meter is a meter. And he goes, no, you might want a long meter stick because I see you're tall. And I go, what are you talking about? Well, the long meter stick to a physicist is 2 meters long, but I think, and scales, old manual scales, instead of ones that are hooked up to the computer, all kinds of stuff that they are more than willing to part with. Beakers, graduated cylinders, like, if you wanted to do that. And in fact, if you get a glass graduated cylinder and you're a little leery of drilling holes in the bottom, you just ask them, oh yeah, no problem. They love helping, and you're probably the first math geek that ever went over there when you do that. And and maybe get another faculty in the department involved. That was the other thing possible. So I want to really thank you. This has been enlightening, and you certainly haven't poured water on our enthusiasm, that's for sure. So.
Yeah, well, I appreciate you guys coming out on Friday night, and hopefully you got something out. And I mean, if you want to see the paper, I'm happy to send it over. Just send me an email, tom.clark@Dordt, and can send you the paper.
Tom does really good things, and you've got about, what did you say, 40 students a year at least, or in this 2 sections?
I think I have usually between 50 and 60 in the 2 sections, but then not everyone filled out the survey. So I think I got about 43 in the survey data, something like that, if I remember correctly.
So Dordt, I mean, is a university.
It is now, yeah. We were a college for, 40, 50 years, and then they upgraded us 5 years ago.
How big a student body is it to have that many students taking differential equations?
So we've got about 1,400 undergrad, and then there's about yeah, 60-ish, 50 to 60, and it's mostly engineers. So we got a pretty big engineering program. There's probably, yeah, 200, maybe 200 engineers out of the 1,400 students.
Oh, okay. So it isn't just the small liberal arts college. It's one embedded with an engineering offering as well.
We have an engineering program in,
Okay.
yeah. And so that's kind of a lot of students come here for that. And so then I teach a lot of differential equations. Yeah.
Gene, oh, Gene is going. Okay. One other thing is that if you have engineering, they have real toys in their labs. So I was doing one on vibrations, and they have what's called a shake table that you can tune to any frequency. And we were studying tune mass dampers and structures like that. And
Okay. Yeah.
they don't let out some equipment. I mean, they're not going to let out a giant piece of equipment because, number one, they know you're, at least for me, I'm this theoretical math geek. But secondly, it's big and cumbersome, and you're better served working it in the lab. So I did independent studies with students, and they again, the lab technicians are more than willing to help do that. And if you start asking around, you find out they've got some real toys. So this shake table, you can set the frequency at which it vibrates and watch the structure until it finally hits its natural frequency and really goes bonkers on you.
Okay.
Do all kinds of studies. But yeah, I think you're to be commended for collecting the data, for getting the students involved in collecting the data. And then you get to experience that euphoric joy every semester when they look at it and they go, wow, look at that, how good that is,
Yeah. 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 There was one, I think it was, I can't remember where I saw the talk, but somebody was doing one on these bending Euler beams. There's a really nice paper on it. I think it's in Simiode. I wish I could remember the name.
From Oregon Institute of Technology. Tierney Fogarty was the author. Yeah.
Yes.
Conference.
And I did that and we did Laplace transform on it. And I had these engineers, they were hanging weights and they were predicting and gathering data. I mean, it was just, you just give them something real and they can't help themselves.
Yeah.
But the engineering department, because you need to calculate like the Young's modulus, and they'll like take your thing and they'll like pull on it with this machine and they'll give you the Young's modulus of the material. And it's just, yeah, they got all the good toys over there. So,
okay. Well, thank you very much.
Yeah, we're probably missing the next talk, so we should maybe jump out.
Well, no, there is no next talk.
Oh, okay.
This is the end of the day.
And this is the last one. Okay.
So if anyone has any questions, Justin or Emma, Justin does.
I think he's just giving a clap.
Oh, okay, that's a clap.
Nice job.
There you go. Okay, well, thank you all very much. And thank you, Tom, especially for the enjoyable feeling that you get, which you translate to us very well, especially whether we've done it or not. I felt it in the presentation. Thank you very much.
You bet.
So take care, and we'll see you all tomorrow. Okay.
Yeah.
All right. Good night.
Thanks for coming.
Thank you.